Today I want to talk about the potential method for amortized analysis, and I will do so by the example of a multi-pop stack and a binary counter. I previously made a video about the amortized analysis, but there I only talked about the aggregate analysis and the accounting method. And so now I want to talk about the potential method. If you haven't seen the other video yet, there's a link above and in the description below. I recommend looking at that one first, because I will build on it, in particular build on the accounting method. But I will also give a short reminder of the accounting method at the beginning by the example of a multi-pop stack. So if you have seen the other video, you can skip this first part. Okay, so let's start with a multi-pop stack. What is that? So first of all, we have the regular stack operations. So we have push, adding one element to the stack. So for instance, I'm now pushing the 6 here. Pop removes an element and returns it. And then I also have multi-pop, and multi-pop does exactly what you would expect it to do. So it has a parameter k, and multi-pop pops k elements. Yeah, so for instance here, if I call multi-pop this parameter 3, I would remove 3 elements. And if there are fewer than k elements, then let's say we would simply do as many elements as we can. So how efficient can we implement all of this? So using a standard stack data structure, so for instance, either a linked list or a dynamic array, I can implement push and pop in constant time. Yeah, so here you see a simply linked list, and there I can simply access the top and push and pop things in constant time. If I use this data structure, then the multi-pop will take of as many elements as I'm popping time, and that's either k, or if the stack doesn't have that many elements, then as many elements as I can pop. The question that we want to address with amortized analysis in the case of the multi-pop stack is if I have a sequence of n operations, push, pop, and multi-pop, starting with an empty multi-pop stack. How long do these n operations take? And of course, push and pop takes constant time, so those in overall will only take linear or of n time, but multi-pop does not take constant time. So it's not that obvious how to handle that, but with amortized analysis, we can show that n operations of push, pop, and multi-pop take overall linear time. So before we do this with the potential method, let's look again at how we did it with the accounting method. The accounting method works with costs, actual costs of operations, and then amortized costs. And we think of these costs as points, or tokens. If I look at the actual cost, then push and pop is constant. So there I simply say they cost 1 coin. Of cost 1. If I look at the multi-pop, then it costs, let's say, k. Yeah, so k coins are needed for a multi-pop with parameter k. Now we want to have the following invariant. We want to store with every element that we put into the multi-pop stack a coin. And for that we assign amortized cost to the operation. So amortized cost is how much do I invest with this operation into the multi-pop stack. And the first operation to look at is push. So push, I will assign amortized cost of 2, because I need 1 coin to pay for the push itself. And then I want to save 1 coin with the element that I push. So if I push 8 here, for instance, then 1 coin is stored with 8, and the other one pays for the push. Yeah, so therefore, amortized cost of push is 2. Amortized cost of pop then is 0, because I don't need any extra coins. If I want to pop, now if I do pop here, I would remove the 8, but there's a coin stored with 8. And I can use that coin to pay for the pop. Likewise, multi-pop also has an amortized cost of 0, because if I want to do, for instance here, multi-pop 2, there were 2 coins stored there. So I can use those 2 coins to pay for the 2 coins that the multi-pop costs. So I can pay the actual cost of the multipop, and I don't need to have any additional coins that I place there because I already have the coins that I would like. So now we have the three operations, push, pop, and multipop. We have amortized cost assigned to them 2, 0, and 0. And these are done in such a way that with the amortized costs that I invest, I can always cover the actual costs. Yeah, so I always have enough coins, no matter which operation comes next, to pay for it with the coins that I already have saved, or with the coins that I'm now new investing in the case of a push. And from that, we can conclude that the running time of a linear number of push, pop, and multi-pop operations, so n operations, starting with an empty stack, takes O of n time. More specifically, the amortized cost of each operation is constant. And why can we conclude that? Because of the invariant, we know that the number of coins that we invest are sufficient to pay for all the actual costs. So stated differently, what we have here is that the sum of amortized costs is larger or equal than the sum of actual costs. That we get from the invariant. Additionally, we know that the amortized costs are bounded by 2. I mean, they're 0 or 2, so they're bounded by 2. So if I put this together, then I can say that the sum of the actual cost, which is bounded by the sum of the amortized cost, so that we know that the amortized cost, those I can bound by 2. Then I have a sum over 2's, n 2's is 2n. So I know that the sum of the actual cost is bounded by 2n. So that was, in very short, how we do amortized analysis with the accounting method. So now I want to move on to the potential method, but let's have a look at kind of the general setup that we had in the accounting method, and then we'll see how we vary it or how the potential method is different. So we have these data structures, d0 to dn, and we change them by doing the operation. So we do n operations. So starting with d0, we do the first operation, have then d1, and so on. Yeah, so we have this sequence of data structures. The I is the data structure after the ith operation. We have the actual costs of the operations. So Ci is the core actual cost of the ith operation, and Ci hat is the amortized cost of the ith operation. And now, depending on whether the amortized cost is larger or smaller than the actual cost, we either save coins or pay with saved coins. Yeah, so if the amortized costs are larger, then it means we can save coins, namely amortized costs minus actual costs. And if they're smaller, then we have to pay with coins, which we hopefully then, we have to guarantee that we then already have saved them. Initial credit typically is 0. And essentially the invariant that we want to maintain is that the saved coins that we have currently, that should never drop below 0. So that's a general setup. So now, how does the potential method differ from the accounting method? So what we did in the accounting method was, for every operation, we assigned an amortized cost. So we decided what is the amortized cost of this operation. And then with those amortized costs, which we had set, we had to check whether the invariant that we have enough coins to pay, that is maintained. We wanted to guarantee that at all times the sum of amortized costs is larger than the sum of the actual cost, or the sum of amortized cost minus the sum of actual cost is non-negative. So how do we get to the sum? The coins that we save in step I, that is actually Ci hat, so the amortized cost of step I minus Ci, the actual cost of step I. Yeah, so accounting method, we assign amortized costs, and then we have to see whether we have enough coins saved up during the process. The potential method, instead of looking at how many coins do I put in, I look at how many coins do I have stored. Yeah, so what I'm saying is how many coins are saved with the data structure after step I. And that is my potential. Now, this is what I define. And then from there, I have to calculate the amortized cost. Yeah, so if I know what my potential is, then from that I can compute the amortized cost of the ice operation. Namely, and there we look at what we had up here. We said that the coins that we're saving in the ice step is amortized cost minus the actual cost of the operation. So that's what we're saving. So if I bring the minus ci onto the other side, what I have is that the amortized cost for the ice operation is the actual cost plus the coins saved in step I. So the coins saved in step I can express differently. Namely, that is the same as the change in the potential. Yeah, so I was saying that after operation I, the coins that I have, that's this potential. So if I want to know how many coins I'm saving in one step, then it's how much the potential changes in one step. And this can be written like this. And now we have our expression for the amortized costs. So the amortized cost of the ice operation is the actual cost of the ice operation plus the change of potential, and the change in potential is potential of the data structure after step I minus potential of the data structure after step I minus 1. Once more, accounting method, we define amortized cost, we have to check the invariant, or we have to check that we have enough budget. Potential method, we essentially define what our budget or what our savings are, and then have to calculate the amortized cost from there. So the first step in the potential method is always defining the potential function. The potential function goes from the set of the data structures to the non-negative real numbers, and a potential should always be defined in such a way that the potential for the data structure after step I is at least as large as the potential at the beginning, and typically the potential at the beginning should be 0. Okay, so you can vary a little bit from this, but this is kind of the standard setup. Okay, so let's have a look at how this works for the multi-pop stack. The potential says we want to say how much do we need to store with a data structure after step I. So how many coins should we save with a multi-pop stack? Now, so looking at this stack, how many coins should I be saving? We see it's 3, but why 3? 3 is the number of elements stored in the data structure I. So that's my potential. So I define the potential to be simply this. Now I have to check the conditions. I have to check that my potential does not drop below the initial potential, which is 0. Okay, so this is a valid potential function. Now, from here, I compute amortized costs. And as a reminder, what was the amortized cost? How would we get it? From the actual cost plus change in potential. Change in potential is potential of di minus potential of di minus 1. Let's have a look at this for push. So the actual cost of a push is 1. Okay. And we simply add an element. Adding one element means that the number of elements stored in di goes up by 1. So the change in potential is 1. Now the potential goes up by 1, so the change in potential is 1. Meaning the amortized cost, which is actual cost plus change in potential, is 1 plus 1, 2. And so we get an amortized cost of 2. And if you look back at the accounting method, that should not come as a surprise, because there we defined it to be 2. Here we derive it to be 2. Okay, let's have a look at pop. Pop has an actual cost of 1. How does the potential change? By pop, I remove an element, so the number of elements drops by 1. So the change in potential is minus 1. So actual cost plus change in potential, 1 minus 1 is 0. Pop has an amortized cost of 0. Let's do multi-pop. So in multi-pop, we, for instance, here remove 2 elements. So the actual cost corresponds to the number of elements removed. And the change in potential is, so the potential drops by the number of elements that I'm removing. So it's minus the number of elements removed. So now again, actual cost plus change in potential, 0. What we now have is we defined the potential as being the number of elements stored in DI, and we derived that the amortized costs are 2, 0, and 0, so they are all constant. So now from all this, I can conclude that the amortized cost, okay, the amortized cost is constant, and the actual costs, which I can bound now by the amortized costs, are bounded by 2n, so by O of n. Okay, we have to be slightly careful here because now I'm claiming actual cost smaller equal amortized cost. And I'm saying this is true because the potential after the ends operation is larger equal the potential at the beginning. But that we should have a closer look at. So, and this also explains why we have this condition that the potential for DI should be larger equal the potential of the initial data structure. So what we want to prove is that the actual costs are bounded by the amortized costs. What we have is, so the amortized cost, if I have the CI, this is simply, as we know, this expression. Now I can write this as two sums. So I once have the sum with the CI, and then I have the sum with the change in potentials. Okay, so these first two terms, they already look good. The expression that I still have to handle is this sum here. But what we can see is that this is a so-called telescopic sum. What does that mean? If you look at the various terms in the sum, so if I do I is 1, then I have potential D1 minus potential D0. Then I have potential D2 minus potential D1 and so on. Let me just show it here, then it's easier to see. So this is the first expression, second summand, and so on. But the important part here is that this term occurs twice, here positively and here once negatively. Yeah, so I have this and that, they both cancel out. Likewise, the second one cancels out with that one and so on. And this goes through the whole sum. And the only two terms that remain is the potential of Dn minus the potential of the D0. So let's write that. We have, of course, our first term, the sum of the CI, and then the only two remaining terms of the second sum. Okay, so we had this condition that the potential should always be of DI should be larger or equal to the initial potential, the potential of D0. This is in particular true for the potential of Dn. Therefore, I have, if I bring D0 to the other side here, I have that potential of Dn minus potential of D0 is non-negative. And therefore, if this is a non-negative term, all of this together is larger equal what I get if I simply drop this term. And if you look at what we now proved, we now have the actual costs are smaller equal the amortized cost. Yeah, so we only need this condition and then calculate the amortized cost, and then we are done. Let's see that by a different example, namely the binary counter. So quick reminder, what's a binary counter? So we have a k-bit binary counter. We represent the numbers in binary. So 0 simply zeros, 1 as least significant bit 1 here, and everything else is 0. So 2 here, we have here 0 and there 1, and so on. The operation we're looking at is increment. So we always do plus 1, plus 1, plus 1. And we are interested in how much time it takes to do n plus 1, so n increment operation. And for that, we look at increments individually. And the cost of an increment corresponds to the number of bits flipped. Yeah, so from 0 to 1, we just need to flip this 1 bit. From 1 to 2, we have to flip those 2 bits. And that's here marked with this blue. And then from 2 to 3, we only have to flip 1 bit, and so on. And as we see, the longer we go, at least sometimes, the more bits we have to flip. So the cost of an operation is the number of bits flipped. And if I have a k bit counter, then in the worst case, that's O of k. So if I now do n increments and simply do the worst case bound of O of k, I would get as running time for n increments O of k times n. What we want to show is that this actually takes linear time, O of n time. Again, it's a case of amortized analysis. We should look at what makes an increment expensive. So let's have a look which increments are expensive. So here the increment, if I go from 7 to 8, I have to flip 4 bits. So why do I have to flip 4 bits? Because I see a 1 here, and the 1 becomes a 0 and push the 1 further. And then I have another one, and it stops as soon as I see a 0. So to answer the question, what makes an increment expensive? If I have lots of 1s beginning at the least significant bit. Then what happens during such an increment? Again, looking at the 7, it's expensive, but all of these 1s become 0s. This 0 becomes a 1, and then I stop. So now we have to think about what is a good potential function. So how should we define our potential? So what would you say for this example? This is a data structure after 23 increments. What should the potential at this point be? So 1, 3, 4, or 5. So the potential should be ideally 4. So why should it be 4? Because we've seen that 1s are expensive. So if I have 1s, then they may cause me to do additional bit flips. You might have answered 3 here, which would be kind of a natural answer because I have 3 1s here and then a 0. But eventually, if I do enough increments, then this one will also play a role. So therefore, the potential here is 4, namely the number of 1s. The potential function we set simply to the number of 1 bits. Expressed differently, so we had written everything in bit counter with AIs. So if my bits are in this array A, then I can simply write this as a sum of the AJ, counting up to k. Now, because either they are 0, then they contribute nothing to the sum, or they are 1, then they contribute 1 to the sum. So that's a different way of writing this potential. Let's check our conditions. The potential initially is 0, that's good. And the potential stays above 0 or 0. Yeah, so it's no negative, because if I count the number of 1 bits, okay, that's at least 0. So we have a valid potential function. Now we just need to calculate the amortized cost. So let's have a look at the ICE operation. As a reminder, amortized cost we can calculate as actual cost plus change in potential. So the actual cost corresponds to the number of bits flipped. Okay, so here we have an example. This is still my 23 example. The number of bits flipped here is 4, and that is these 3 ones, and that's 0. I will write it as the number of bits that I have to flip from 0 to 1. So that's this first one here, and plus the number of bits flipped from 1 to 0. So those are these 3 here. Now, the number of bits flipped from 0 to 1, that is always only 1 bit. So there's leading 0 here, which is now 1. And then I have the bits flipped from 1 to 0. So those I simply have to count here. So the actual cost is 1 plus number of bits flipped from 1 to 0. Now let's have a look at what is a change in potential. The change in potential corresponds to the increase in the number of 1 bits. How does a number of 1 bits increase? So first of all, anything that goes from 0 to 1, that contributes to the potential. And everything that goes from 1 to 0 is now less in the potential. So I get number of bits flipped from 0 to 1. Those go positive into the change in the potential. And then those that go from 1 to 0, because now these 1 bits are gone, those go negatively into the potential. Therefore, I have a minus sign here. Now again, I know number of bits flipped from 0 to 1, that is just 1. So this sum now looks like 1 minus number of bits flipped from 1 to 0. Let's put this together. Amortized cost is actual cost. They have 1 plus this term plus change in potential. They have 1 minus this term. Yeah, so if I do 1 plus that term plus 1 minus that term, then obviously these two cancel out. I have these two ones left. So just the ones remain. So I get an amortized cost of 2. So starting with our definition for the potential, we now derived that the amortized cost is 2. And we can immediately conclude that the worst case running time of n operations is O of n, because amortized cost per operation is constant. And we have that the actual costs are bounded by the amortized cost. So this now follows, as soon as we proven this condition here, we can conclude this fact here. So here this proof is really immediate. So what have we seen? We've looked at the counting method to then from there go to the potential method, and the examples were multi-pop stack and binary counter, and that's all for today.